Okay. So I'm going to talk about the Red Sea mainly. There's been a broad interest in the Red Sea because perhaps it's a classic example of a plate, a continental plate that has been rifting and turning into a new ocean basin. Perhaps it's an analogue for the South Atlantic and other rifted margins. So I'll talk through that background and motivations in a moment, go through why we might be interested in it. I'll then go through some of the results we've got looking at the crustal type. Is it continental or oceanic crust? And then I'll look at the morphology of the evaporites. And I'm going to suggest that the flowage is connected to the crustal type because the flowage is controlled by basement geometry. So there's an interesting connection between the surface geomorphology and the underlying crust. I may kind of flip between these two a bit because they are, it's going to confuse people a bit. So I may flip between these two subjects a little bit, but the reason is that they're very strongly connected with each other. And then at the end, I'll just mention that with 2 or 3 slides, the seismicity. The northern half of the Red Sea has remarkably low rates of seismicity until you get to Sinai. And I'm not sure we understand why, but I'd just like to highlight that observation. So before I start, I'd like to acknowledge a few people, 2 PhD students. When he was a PhD student, he's now gone back to China, and Oki, both been doing some really nice work with me. I actually started getting interested in the Red Sea when I went on the Italian ship, Urania, with Marco Ligi and Enrico Bonatti, that invited me along on one of their cruises. And so thank them for getting me started. There were some inputs from Ian Stewart, who's based in Australia, and Zeldin, who's an interesting Sudanese senior scientist. So the Red Sea, I'm sure most people know where the Red Sea is, Red Sea between Arabia and Africa. The Red Sea is interesting because of this pan-Arabian African shield that has split, and within that region there was a period of extension, and then seafloor spreading has started. However, the stage that we're at is still controversial. The data sets available haven't been perfect. The southern Red Sea, at least along the axis, I think is widely thought of as oceanic. The northern Red Sea has been thought of, or been suggested to be stretched continental crust by Jim Cochrane, although you will have, if you read the literature, you'll see there are now other ideas that this may be oceanic as well. I'm not going to talk about that really. I'm going to talk about this central Red Sea area, which is has been suggested to be transitional. We'll look at that, whether it is transitional or not. So the reason why you might want to know about the Red Sea, so this is a numerical model of continental rifting by John Armitage, and it was intended to represent the Seychelles India rifting, so not the Red Sea, but it illustrates some of the processes. So you have during extension, you'll have thinning of the lithosphere, and the mantle underneath will rise and undergo adiabatic decompression and melting. And people have been interested in margins, trying to image the amount of melt that's produced, and maybe you can link these models with those observations. But those observations have almost entirely been on old margins. Wouldn't it be nice to know more about this process as it occurs in a modern setting like the Red Sea. Perhaps we have a basin that's in this stage. So the other reason why we might be interested in the Red Sea is because it has very thick evaporites, up to 4 or 5 kilometers thickness in places. And so this is a cartoon of the Red Sea from very old work by Ron Girdler, Bob Whitmarsh. So it's published in the DSTB volumes. So what we see at the present day, we can quite often see oceanic crust exposed at the center, and then these thick evaporites, which appear to be flowing inwards. And in their view, the flowage was driven by the extension. As the plate is separating, the evaporites are flowing in to fill the gap. This is kind of giving away our story a bit, but this is the structure we anticipate for the central Red Sea at the end of the Miocene, with oceanic crust in the center and stretched continental crust towards the coast. The evaporites will have lain at a much higher level. Because this is oceanic lithosphere, the subsidence rate here is higher than it would be on older lithosphere. So that's going to generate a rotation in the evaporites. So the flowage that we see, we'll come on to that later, is driven by lithospheric subsidence and extension. So these things should be processes that we can look for in some of the older margins, and indeed some people have already. So perhaps the Red Sea is an analogue for the many other salt provinces that have been found around the Atlantic and the Gulf of Mexico, or some of them. Some of these may have been interior seas, but for the situations where we have a margin and thick evaporites deposited during the rifting phase, perhaps the Red Sea could be an interesting analogue. The reason why, so we might be interested in the Red Sea because it's young and the structures are much shallower, much less destroyed by diaparism and more accessible. This is a seismic image of Brazil, and this is the whatever was underneath the salt. These are the salt diapirs. So the material off Brazil is much more highly mobilized. We don't know the timing of events so well because it's not been drilled. We don't have the chronology so well known. But Ian Davidson has suggested some things that we see in the Red Sea, like the diapirs began to grow during salt deposition. This is something we see in the Red Sea, and he suggests there's evidence of downslope salt drainage, gravity flowage of the salt or evaporites, and that's something we see. So some people have drawn really direct analogies between the Red Sea and the South Atlantic, and I think that's actually not appropriate because they have differences, quite important differences in the timing of the evaporite deposition compared to the crustal stage, whether it's a continental or oceanic rifting stage, and the rifting rate is different. So there are big differences, I think. But what we can do is look at the Red Sea, investigate the structures, and where we see things that are interesting, maybe we can use that knowledge when we go and investigate higher resolution seismic data sets and so on from these other margins. So if we now come to the crustal structure, and I'll give the alternative view. This is not our view, or my view. This is the Italian, I guess, American view. And this isn't a criticism, actually these are my friends, so I'm not going to, this is not a personal criticism at all. Enrico and Marco Ligi have the view that a lot of the Red Sea comprises highly extended continental crust. This is the bathymetry of the Red Sea, and we see these close contour depressions that are called deeps. Between them are these zones called intertrough zones. The deeps contain mostly basaltic lavas. If you dredge these areas and take photographs, they have basaltic lavas, and their compositions are like mid-ocean ridge basalts, and these areas have high magnetic anomalies. So, and you can't see them in here, but you can identify in some of them the reversals that you would expect from seafloor spreading. So there's no controversy that there is likely oceanic crust now in these areas. The problem occurs outside, where we can't see what forms the basement, where everything is actually covered in these evaporites. So Enrico and Marco's view in this cartoon, going from the north to the south, in the central Red Sea, you only have seafloor spreading in the deeps, and between the deeps, you may have continental lithosphere, continental crust, sorry. And in the far north, where Jim Cochrane would say we have highly stretched continental crust. So that's I say the Italian-American view. So I'd just like to outline evidence, I think, that it's actually oceanic crust underneath these evaporites. So I'll go through a series of slides, which hopefully will convince you, or at least give you food for thought. So a big improvement has been in the free air gravity anomalies that David Sandwell and others have got from satellite altimetry measurements. They've improved the algorithm, so we're getting much better data in interior seas like the Red Sea. In this image, I've just taken the free air anomalies and shaded them from the northwest. So what you're seeing is a series of apparent ridges in free air anomalies. The seabed is relatively flat away from the deeps. So away from the deeps, at least, what you're mainly seeing is possibly the basement topography in these. And you see these ridges that are crossing the Red Sea, not quite straight, maybe somewhat V-shaped. Some of them align with features on land. These look somewhat like the ridges that you get at mid-ocean ridges. So this is the Southwest Indian Ridge, where magmatism at one point has produced a ridge off axis, also somewhat V-shaped, and fracture zones and non-transform discontinuities. The plan view structure is similar. When she has investigated the rugosity implied by these fluctuations in gravity anomaly, so what he's done is inverted the fluctuations you see along these lines using the Bouguer slab formula. So you invert for a basement topographic roughness, which we express as root mean square value. When you do that, you can do it with where you assume the density contrast is either of an oceanic crust, perhaps a Grobroic type density, or continental crust, a lower density material. When you do that, you find the rugosity is actually not so different from what we see in slow spreading ridges. These lines are drawn from the Mid-Atlantic Ridge. This isn't evidence by itself that it's oceanic. It could be a coincidence, but at least it's consistent. Zeldin, I've introduced earlier, who's a Sudanese scientist, for his PhD, which he did in Strasbourg in the 80s. Zeldin studied deep seismic reflection data collected along these lines collected by a commercial company with quite a long streamer. So actually, originally they were high quality data. Unfortunately, we no longer have the digital data. Zeldin has shared with me paper records with his interpretations overlaying. So what we've done is digitize his interpretations, depth converted them. Wen has verified them using a magnetic source depth calculation, Venner deconvolution calculation. So that's what you see in these gray circles. And what you expect in Venner deconvolution is that all the sources cluster beneath the basement, and that's roughly what they do in most of these. So it confirms the basement reflection. But anyway, so what you see here is a high underneath. These are the free air anomalies underneath. It may be confusing just looking at the free air anomalies. What we actually have under here is a basement high. It's not a valley as you would expect with a continental rift. So it's similar to a high that you'll see on mid-ocean ridges near hotspots. So this is the Reykjanes Ridge near Iceland, and we get this high. That's what we see in our seismic data as well. And the analogy is actually better with the Southwest Indian Ridge near hotspots like Bouvet and the Spice Ridge and so on. But anyway, you see this high. This is typical of a mid-ocean ridge, somehow influenced by a hotspot or a change in magmatic content. And what Wen has done here is plot Bouguer gravity anomalies in blue over, we've rescaled it. And you see there's this remarkable correlation between the basement reflection depths and Bouguer anomalies in the axis until you get closer to the coast, and in many places the correlation breaks down. The basement reflection rises towards the coast, but the Bouguer anomalies are flat or may even go down. So this is a clue that there's a different density structure nearer to the coast, which we think is stretched continental crust mainly. What I'm showing here is the implied density contrast by these correlations. It's actually a bit lower than we would expect for example, gabbro with evaporites. You'd expect a higher density contrast. So this may be a clue that what underlies here also includes thickened crust under the axis, and an effective temperature of the mantle underneath. But anyway, we have this interesting correlation, which I will use later. I'll come back to that. Wen's also looked at roughness across axis. Typically at mid-ocean ridges, you have a roughness due to the faulting and magmatism. And people have studied that at mid-ocean ridges, quantified it. We've tried quantifying it here. It's difficult to do because you have to choose a separation wavelength between the roughness and the morphology of this high, and we've not the reviewers of this criticized us for that. So anyway, so you end up with very large error bars. However, at least it's consistent. The value we get is consistent with other slow spreading ridges.
I think we lost Neil. We'll have to wait for him.
Yeah, yeah. Hi, Neil. Are you still there, Neil? Okay. Yeah, I guess he's just lost his connection or something.
I think we just have to wait for Neil to come back. If
Yeah,
anybody-
I guess. Yeah, I guess. You see, I think he's officially left the chat, so I assume he's just trying to reconnect.
Well, if anybody wants to say hi to each other who hasn't seen each other in a while, they can do that while waiting. We should have some kind of like, when the television, it doesn't work, you could have they put on a little blank screen and some music so that people don't get bored waiting. They know that things are still happening.
Some nice elevator music. Yeah.
Yes, exactly. Please wait. Technical problems, but we'll be right back.
Yeah, what I find interesting that how much they can derive from bathymetry. That's very impressive.
And I had a question, I might as well just ask it now because it's sort of their assumed density contrast that has to do with trying to make their Bouguer depths fit their reflection depths.
No idea. I think it was magnetic. He's trying to get the magnetic fit something.
Yeah, but in the latest one, he was showing his Bouguer, his depth according to Bouguer and how well it fit the reflection depths. And then he had something to do with the density contrast. And I was trying to figure out how they got the density contrast. And I was thinking maybe it was they were trying to make it so that the Bouguer depth corresponded to the reflection depth. They had to do a certain density contrast, but I don't know.
Yeah. Yes, other thing he has not taken into account, and we'll discuss when he comes back, is the role of sediments coming in, apart from the evaporites, because we're on the marginal basin.
Does anyone have his phone number?
I think
He's coming in.
Hello.
Yeah.
Sorry.
Okay.
Sorry. We live up in the hills, so I think that maybe a sheep had been biting through the cable. Okay, leave my video on. Sorry, but I'm not sure where I got to. So here, I think.
No,
I think it's the previous slide.
Okay.
We hadn't seen that one.
Yeah.
Okay, come back.
Oh no, this one. Yeah.
We
Yeah.
saw that
Okay.
one.
Well, so the point of this is ordinary mid-ocean ridges, you get this up and down in the topography due to faulting and magnetism. And so Wen's tried to characterize the RMS variation in this. And so we get a value that is like an oceanic variation, but with large error bars, it's quite hard to calculate because you have to choose a separation wavelength between the large scale geomorphological feature, the ridge, and this fluctuation. And we actually got criticized by reviewers for that because it's not the same method as their methods, but it's just that's just the way it is. This isn't evidence that this is a mid-ocean ridge, but it kind of says that it's not that the data aren't surprising, that it would be consistent. Fairly conclusive evidence comes from some quite old seismic refraction experiments. So the group in Hamburg did a set of OBS experiments with explosives, and they interpret their data as showing an oceanic crust and then a continental crust nearer to the coast, which is how we interpret the gravity data. Going back even earlier, Tramontini and Davis did an experiment with sonar buoys and explosives, and their lower layer velocities are what you could say are consistently layer 3 velocities. So I think a lot of the stuff, the crust under the axis is oceanic. And going back to the magnetic anomalies, these are from the 70s.
Looks like we've got lost Neil again. If he turns his video off, another sheep. If Neil turns his video off, right, he can still share his screen.
Yeah, but we have to wait for him to get back. He's off now.
Yeah.
You don't have a copy of his thing, because you could also present it, and that way, at least when he goes away, if he goes away, we still have the images.
Yeah, no, I've not. I don't have a copy of it. I could ask him to send it me. I mean, he was fine, right, for half an hour. So yeah. I guess maybe see if it improves if he just turns his video off. Oh, he's back. Oh no, that's not Neil. Hi, Neil.
Hello again. I hope it stays on.
Yeah.
So this is something that Jerome Dimon has looked at. He's had access to a Saudi.
I think maybe just go back one slide, Neil. Hi, Neil.
Hello again.
I'm not. Yeah, I'm not. Yeah, it seems to just keep cutting out.
Yeah.
Not really sure what to suggest.
I don't think I can do anything here apart from just keep going and
Well, I mean, one option would be to send the presentation to Alex and have him present, and you can also connect to Zoom by telephone if it cuts out again.
okay.
Uh,
My phone won't do Zoom. I'd have to just do
Ah.
an ordinary phone.
okay. I mean, well, it worked, didn't it, for half an hour? So
Yeah.
I mean,
Let's I'll just try to go fairly quickly then and just try to do it. So anyway, the magnetizations are actually fairly large, as you would see at a mid-ocean ridge. So what Oki's done here is found the peak-to-peak variations, and when you plot those peak-to-peak variations, you get a decay that looks a bit like a mid-ocean ridge. We actually don't think the decay should be the same because the evaporites would have covered everything earlier. So we don't expect alteration of the basalt in the same way as you would get in a normal mid-ocean ridge. But anyway, it shows this decay that's fairly normal. This is interesting, I think, in that what Oki's done is calculate the east to west gradient of the magnetization. So these result of the inversion. And the reason for doing that is you boost the high frequencies. And you see at the axis, there's very high frequency, typical of mid-ocean ridge, but then there's this change to lower frequency. And these are cross sections showing this change from high frequency to low frequency. What he's showing on the right is a theoretical set of magnetization gradients. This is obtained by using the opening rate of Africa, Arabia, and the geomagnetic timescale of Candy and Kent. Just made a series of polygons, and you see you'd expect high frequencies all the way out to here, and it's very different from this. So our interpretation is that this transition represents the point at which the spreading centers got exposed. And so you're seeing, so before then you had intrusion of sills in here, not a normal spreading center process. And there is an issue of depth to basement. So there's also you'd expect frequency to change going this way because the basement gets deeper. So we've investigated that by taking these theoretical anomalies, work out the magnetic anomalies, so the magnetizations, work out the magnetic anomalies that would be produced by those magnetizations, and then invert again for the magnetizations. So this reproduces the effect of depth to basement. So these steps are done with the basement depth. And you'll see that there are still you'd expect high frequencies in here, and it looks very different to this. So it's not a depth effect. So now quickly go over the evaporite flowage. What's interesting in the central Red Sea is the density of all the stuff that's above the evaporites. The evaporites themselves comprise halite and hydrite and shale. And then above them in these drill sites, 225, 227, you have the Pleistocene sediments, about 200 meters roughly thickness. The densities of these overlying sediments are similar to halite, so we don't have a density inversion. So diaparism is suppressed. You don't have normal diaparism that you do get at the margins. So this is a 3D view of the uranium multibeam data looking into the Thetis Deep region. This is the volcanic gemomorphology, so volcanic cones, ridges, and faults. And then you see these big flows entering the axial valley. In some places they're blocked where the basement is higher, flowing around these. The flows have rounded fronts, much like other viscous flows. In the north here, this is one of these intertrough zones where the evaporites have flown in and met coming from both sides, and you appear to have compression folds. Here I'm showing the top of the evaporites determined from shallow seismic reflection data. And what you see in the areas, this is one of these intertrough zones. Where we have the intertrough zones, the evaporites on the flanks are a bit deeper. And this is simply just reflecting the compensation. So as evaporites have flown into here, this has subsided. On the other hand, where the evaporites haven't flown in, they lie at a higher level. And the image I've just shown you is in here, basically. So the evaporites flowing into that intertrough zone in here have left these areas that are apparently deflated. On the right, I'm showing Bouguer gravity anomalies. And this is the ridge, basically. And in these areas where the Bouguer gravity anomalies are depressed, this is effectively a fracture zone in the underlying oceanic basement. And if you look, you'll see that there are three major fracture zones, this one, and this one, and they all underlie where the evaporites have flown in and formed intertrough zones. So it seems that the morphology that we see in the maps, these deeps, the deeps actually overlie areas where the evaporites are being held back somehow. And the intertrough zones in between them are where the evaporites have flown all the way in and covered the axis. And this is illustrated here with this 3D view. So what I've done, this is the bathymetry in topography, this Jeddah. If you look along the axis, you have these intertrough zones where the seabed is higher and you see evaporites near the surface in these areas. And then you have deeps in between where you have the basalt. If you look at the basement topography, this is derived from the Bouguer anomalies mainly, you see the intertrough zones overlie the fracture zones and deeps overlie the basement highs. So there's an inverse relationship. If you looked along axis, the seabed is like a mirror of the basement with these intertrough zones, higher intertrough zones being where the basement is deeper. So there's an interesting connection between the oceanic crust, which has made this structure, and the present day morphology and the movements of the evaporites. I worried for a while about the flow velocity because Namakias in Iran move very fast. So maybe 1 to 8 meters per year. If the evaporites did move this fast underwater, you would expect them to flood the axis, and they don't do so. So they must be moving slower than plate tectonic rates. So slower than the half rate, which would be 6 millimeters per year, quite slow by orders of magnitude, 3 orders of magnitude. Why is that? So I worried about this and I've been told not to worry. It's mainly because the evaporites are actually layered, and they have these thicknesses of anhydrite, which make them more rigid than you would expect from the pure halite. We see that in some of our seismic data. We see this layering. So I'm now going to show 2 seismic images. We're going to look at the surface of the evaporites in these, one here and one here. So this is some of the Urania data, and this is an older data set. And so the Urania data from the north show this is what we call the S reflection, which represents the top of the evaporites. Underneath it, you have these dipping reflectors. So this appears to be an erosional surface, an unconformity. On the other hand, down here, in the older data, these are old, but they're actually really good, I think. You see a simple layered structure without erosion. And you should see this is at 1 second two-way time, and this is at 1.5 second two-way time. So this is actually shallower than this. That doesn't make sense really. If one is eroded, but it's shallower, but the one that's not eroded is shallower than the one that is eroded. How can that be? Well, the reason is, of course, that these have subsided much more because of the flowage in towards the axis, whereas these are still held up at a higher elevation. So the unconformity appears to also record this flowage. I've recently been interested in trying to reconstruct the level of the evaporites at the end of the Miocene. So this is the present level of the evaporites, about 900 meters. When I just took the reflection data and averaged a lot of data. I've tried to reverse a number of effects. So lithospheric thermal substance has quite a large effect. Isostatic effect of the water overlying the evaporites and the applied Pleistocene sediments, and the overflowage. So as the evaporites have flown towards the axis, shown by this gray box polygon, that implies that the evaporite surface must have deflated or subsided to compensate for that. So basically some of this has gone into here. So if we reverse that, you see that the evaporites could have been at a much higher elevation. There's another adjustment for dissolution. There's a reverse adjustment because the whole of the region has been uplifting. Arabia has been uplifting. We know roughly how fast that has been happening from uplifted coral surfaces. So when we do this, we find that the evaporites would have lain at 100 or 200 meters relative to modern sea level, so much higher. And this partly explains, I think, why the spreading center would have been flooded by evaporites, because the elevation of the evaporites relative to the basement would have been much greater. So there's more potential energy for that to occur. So finally, just talk about the seismicity. If you look at global maps of seismicity, the Southern Red Sea is fairly typical. A lot of seismicity, a lot of similar range of earthquake magnitudes. But the Northern Red Sea is almost without significant earthquakes until you get up to the Gulf of Aqaba and Sinai. And then, of course, you do get a lot of seismicity that's well known. So I've been interested in why this is. Two possible explanations. Well, one possibility is that the whole area is waiting for a big earthquake. This is a gap with seismic potential, which would be pretty horrible if it occurred. I don't think that is the case, because if you look at historical records going back 2,000 years, there's no evidence of any big earthquake. So I hope that's not the case. Ian Stewart and I suggested that there are possible two effects. One is thermal blanketing. So Fernando Martinez and Jim Cochran modeled the heat flow along this line, and it suggests that the basement temperature would be about 100 degrees C higher than you would expect otherwise. And maybe you do get overpressuring underneath the evaporites. So almost all of this area is covered with evaporites, except where you see these green polygons. So there's a potential for overpressure. This is difficult to accept, because I think if you had overpressure, you'd also have a lot of slumping of the evaporites. So this is my preferred explanation. So I'm just highlighting this observation. It's really curious. So this is the Southwest Indian Ridge seismicity, very frequent earthquakes. And that's what the Southern Red Sea looks like, fairly typical ultra slow spreading ridge. But then we have this really big gap. And when you look at, you convert the seismic moment release to coupling coefficient, you see there is this big step by about a factor of 10 between the north and the south in coupling. This is the opposite to what you would expect. The spreading rate is higher in the south than in the north. So if this was a mid-ocean ridge, a normal mid-ocean ridge, you'd expect higher coupling towards the north. It's the opposite to what we expect. And well, there is some evidence of volcanism. So the B value, when you look at the number of events against magnitude, is a little bit high. 1.22 is my estimate. So there could be some magmatic spreading going on. Though why that would be different from the south, I have no idea. I don't think that's a very good explanation either. So our work continues. This was a cruise led by Nico Augustin and Freuke van der Zwaan on the Palakia, lovely vessel. And we were mapping off Sudan. And again, you see the volcanic geomorphology of the axis with these cones with collapse pits, and this wonderful pattern of flowage into the axis. So I think Nico is getting, so here's Nico, he's slowly getting the whole of the Red Sea covered with multibeam through his cruises and collaborations. So these are my conclusions. So I won't read through them. I think you can see them. It's quite an interesting part of the world to work because it's very hard to get permissions, but through various processes, Italians and Germans and so on have got permission to work there in the past. And surprisingly, there is quite a lot that can be gained from mainly legacy data sets. And I think I'll stop there.
Okay, great stuff. Thanks for that, Neil. If I believe a couple of people had some questions, Wayne and Satish, possibly, which we were discussing while you were away, Neil. If anybody does have questions, if you just put a message in the chat to say that you've got a question, and then we can, yeah, you can unmute yourself and ask your question.
Oh, I could turn on my video again.
Yeah.
Well, there's due to be a new arrangement with Australia that will import their sheep, so we won't have any more sheep into our cables.
Yeah. Yeah. So Satish, do you want to ask a question to Neil? Sorry.
Yeah, it's very nice talk, and you have done quite a bit of work, Neil. I'm very impressed because we started thinking about going to Red Sea 12 years ago and never managed to do anything.
Right.
So it did not discuss the role of sediments because in the marginal rift system, you have a lot of sediments coming from the continent.
Yeah.
Apart from evaporite. So do you have any feeling how much sediments, how much evaporites, and their effect on your whole interpretation?
We've only really looked at the central area, the kind of median area. So yes, there will be a lot of sediments closer to the margins, and you see that in commercial seismic reflection data. You do see thick terrigenous sediment. You see a lot of diaporism. The evaporites get mobilized a lot. I think the structure underneath is a bit hard to tell with the data I've seen. I'm pretty sure Saudi Aramco have excellent data that we, of course, will never get to see, unfortunately, or not use. I mean, I don't really have much idea of the geomechanical role of that sediment. There's still quite a lot that's unresolved, like the symmetry of the basin. If you look at the drainage divides on the two sides, they're actually a bit asymmetric. So that it kind of looks roughly symmetric, but the whole structure is a bit asymmetric. How much? So we do expect more sediment to have been eroded earlier because the climate was quite different, I think. It's not always been dry like it has been today. So there will have been a lot more erosion and material entering the rift. I can't really say much more than that. I don't know, I think is the answer. Should have said that at the beginning.
Are you trying to get something from Saudi Aramco or KAUST, what they are doing? I see Laura is there.
Well, Saudi Aramco are pretty hopeless. I've tried talking with them, and that's really difficult. There is a guy in KAUST who has a copy of some of their data, so we have looked at it a bit. KAUST have a project where they're going to deploy OBSs and do passive recording. So that may at least produce some interesting overall crustal structural maps, but not the details. We'll use high resolution seismic, not capable of really that sedimentary structure. There are bits of data all the way around the Red Sea that companies have collected over the years, but mostly quite a long time ago. So the quality is not so good. So Egypt has there's quite a lot of reasonable data. The salt creates problems for imaging beneath, apparently. So they're still struggling with, there was a recent 2D shoot off Egypt, and I think they were struggling to process the data because of the salt.
Thank you.
Is that,
Okay, Wayne, do you want to ask your question, or do you want me to just read it out, or?
Well, I can ask it. I mean, I think Jan's will probably be more interesting than mine, but at least we'll get mine out of the way. It was just a technical question, which is about when you talk about the density contrast that you got of 300, 400 grams per meter, I think, something like that. Was that based? What was that based upon? I was guessing it was based upon fitting your overall depths with using the gravity with the depths using the reflection, but I didn't know, so I was just curious.
yeah, I mean, we basically just inverted the Bouguer gravity formula to begin with. So Bouguer gravity formula just relates gravity change to elevation of an interface with a density contrast. So we use that to begin with. Then when because you get errors when you do that because it's really simple. So when then did some forward modeling to try to work out the error produced by that approach.
Okay, but that was based, but that was based mostly on the reflection data, I guess. And is your sort of your ground truth or your? Yeah,
it's correlating reflection interface depth with Bouguer anomaly, and you get very strong correlation.
Okay.
Bouguer anomaly, doing that calculation removes the seabed effect, and the sediments above the evaporites are very similar in density to the evaporites themselves.
Right.
So removing the seabed should remove the shallow density effects, and then what you're left with should be the deeper structure.
Right. Okay. Thanks.
Jan, do you want to go ahead?
Sure. Hi, thank you, Neil, for this talk. Very interesting. You mentioned at some point that. All right. You mentioned at some point that it was well known that Saudi was going up, and I was wondering if you could be more specific. I mean, for me, the corals on the coast, most of the marine stages are overlapping each other, meaning that they are not going up very much, and the big scarp is actually further east, and so the coastal area doesn't look going so much upward.
Well, when I reviewed, okay, so the younger corals are the ones that are best dated, and unfortunately, that story is confused with glacial isostasy and sea level fluctuations and so on. So ideally, you'd want like a Miocene coral, and they aren't. They're very poorly dated. So
they're well known in the north, but in the central part.
Yeah, there's some in Saudi Arabia and some in Sudan, and so I just reviewed the whole lot, and my estimate was like 100 meters basically since 5 million years. There's a guy who was in Cambridge who tried modeling the stream profiles. He came up with a similar estimate, but I feel uncomfortable kind of accepting that because the climate's changed a lot. So I'm not sure the stream profile analysis is so good. There of course is this geological explanation, and that you have this in seismic velocity models, you have this hot tongue underneath Arabia that's supposed to be uplifting it, coming from afar. So there's seen in the seismic velocity models this hot material underneath, low velocity. That doesn't tell you how much it's gone up, but there's a reason to accept that it probably has.
Okay, thank you.
Yeah. Satish had a question, I think, again.
Yes.
Sorry.
Looking at what's happening in Ethiopia and Djibouti, if you follow the fault system and volcano further in the south, it seems to get a feeling that there is a extension going on there, which is parallel to the southern part of Red Sea.
Yeah.
Do you see any effect of that in the Red Sea?
Yeah, I wonder if I can find a map. Oops, they're going to let me go back. If I can find a gravity image. It doesn't quite extend. Sorry. Well, here's a gravity image. It's not the best one.
That's where it comes down to where you have a 2014 written.
Yeah. So Richard Gordon had worked with somebody who looked at the magnetic anomalies through here, and there's a change in spreading rate of, I think, about here.
Okay.
So the spreading rate suddenly decreases in here, and you can't see it in here, but there's a bit of seismicity across here. So it appears that there's a triple junction, if you like, about here somewhere, and there's a break. You can't see it in here, but there's also another basin in the gravity data that looks to me like it's an older rift. Anyway, so the present, it seems that there's a split, and this area has been covered with GPS, and there's clearly it's called the Danakil plate. It's moving, it's kind of rotating, and the southern edge of the Danakil plate is almost like it's attached to Arabia. So the whole thing is kind of moving out in like a book. You can imagine books on this splinter basically rotating. Yeah, it's quite interesting that the people in Kaus, Johnny and others are trying to look at this as well, with what we're looking at the earthquakes and with INSAR, I think, on these islands.
Thank you.
Yeah, I think this makes, so people draw these analogies between the Red Sea and South Atlantic, but of course you can't know in advance what these effects will be. I mean, I've even seen somebody trying to forward model something, and you can't know all the processes going on in around afar, all this very complex volcanism and tectonics.
Good.
Yeah.
Is there any other questions?
How did you get permit to go to Sudan?
Well, that wasn't me. That was Nico. We wanted to go to Saudi Arabia, but then some politician in Germany started complaining about the Saudi people, well, military bombing people in Yemen. So had to change tack very quickly. So somehow there was some high-level meeting between people in Germany and Sudan, and then it got sorted out. I think Sudan's interesting because politically it seems to be getting a bit better, and so maybe that will become a place to work in the future. Perhaps easier than Saudi Arabia at the moment.
It looks like we've got another question just coming there. Andrina, do you want to ask the question yourself? Okay, I mean, I could just read it out. Oh, okay. So it's basically from the data you have, where would you expect the pole of rotation to be? This information could help to understand the spreading rate variations along the basin.
Yeah, it's actually already quite well known that it's not my work, but there are magnetic anomalies, I guess, all the way up through here. They get somewhat less recognizable in here. So you have magnetic anomalies through here. You don't have transform faults to use. They all suggest a rotation pole in the Mediterranean. So this is work by Chu and Gordon, is it 91 or somewhere around there. But we also have a lot of GPS measurements, and I forget the guy's name, but they found that the modern day movements are almost the same as the ones you get from the magnetic anomalies from Cron 2A, which is about 3 million years. So it looks like from 3 million years to today, it's been going at the same rate. There is a bit of a problem of working further back in time, and we don't have enough anomalies really. But it looks like if you look at anomalies in the Gulf of Aden, that they haven't changed that much. So it looks like it's been mostly moving in the same direction for the last few million years.
Okay, good stuff. I think I had a very basic question just before we finish. I think you might have explained it, and I think I might have just missed it when you went off. You had the abyssal hills themselves. Sorry, the faults themselves, the fault scarps. Do they in any way, the size of the fault scarps compared to the thickness of the halite? Is it the fault scarps themselves which are holding up the evaporite flow, or is it the actual abyssal hill?
Well, I think where the abyssal hills are higher, then they hold back the flows, and you can't see it very well in here, but you see lineaments in the flows that kind of wrap around. But you also see, maybe you see it a little bit here, the evaporite surface goes down in a series of steps. And in places you can see, here's a step, for example, you can see a fault in where the basement's exposed. So it looks like it's cascading down these steps. Well, here's another step possibly in the flows, and you can see a fault escarpment here.
Yes.
So it looks like, the faults, obviously they have relief of the stuff that's on top of them, but where they're lower, that's where you're getting the evaporites flowing across them.
Yeah, it's a really cool image. Okay, good. If has anybody else got any last questions, or I think we've overrun a little bit. So, yeah. Well, okay. Well. Thanks a lot for that talk, Neil. It was very interesting, and there's some good discussion there at the end as well. So yeah, thanks a lot for presenting the work, and thanks everyone for coming. And yeah, we shall see you all again in a couple of weeks.
Well, thanks for inviting me, and I'll see everybody in the bar afterwards then.
Yeah, if only.
Hey, thank you very much, Neil. Great talk.
Thanks, Satish.
Bye.
Bye.
Right. Yeah. Thanks for that, Neil. I'll yes.
Yeah. Where do I submit my travel claim?
Yeah. Yes. Indeed.
I'm sorry about that. So I have had problems in the past, but it's not usually that bad.
It was strange actually, because it wasn't like it was cutting in or out or anything. It just it just went off all of a sudden. There was no, it's not like you went all jerky, and it just cut out straight away.
Yeah.
But it was fine. We got there in the end. So yeah. Okay, good. Will you be at? I think AGU is in person this year, so we might actually get to yeah, to
Oh, well, I wasn't planning on going, but actually, that's a thought. Maybe I've got travel funds. I could. Don't know. That's a cheeky idea, really.
yeah, yeah. Well, I didn't think it would be, but yeah, it's. I think now that it's on, it'd be good to meet a lot of people. We've done so many of these talks, but had very little chance to actually sit down and chat with people. But
it will be interesting going back to normal face to face. I'm scared of the whole idea of meeting.
Yeah, indeed.
Getting so used to this now, it's going to be quite strange going back to normal.
Yeah, I think I'm ready for it though.
Yeah.
Okay, good stuff.
Well, thanks.
Yeah, well, thanks a lot for that, and we'll speak soon.
Okay, yeah. Thanks, Alex, and everybody. Okay.
Yeah, cheers. Bye.
Stop.